Sometimes you're going to be asked to find an x-intercept, and that's not going to be possible with your school maths. Say, for example, I've been asked to find the x-intercept over here, and I couldn't find it using my existing knowledge. I'm going to show you a new method, and this is called the Newton-Rhapson method. But first, I'm going to show you how the formula was developed. What I do first is I make an estimate, quite close to where I think the answer should be. Then I find the corresponding y coordinate. And then thirdly, I find the gradient of the tangent to that point. As the derivative is the gradient of the tangent, I'm going to write that as f prime at that x value of a1. The next thing that I'm going to do is I'm going to take all this information and put it into the equation of that tangent. We know that the equation of the tangent is the equation of a straight line, which is y minus y1 equals mx minus x1. Now putting in my specific values, I can write this as y minus my y value is f at a1. The derivative is my gradient, and so that's f prime when x is a1. And that must be times by x minus my chosen x value, which I called a1. As I'm looking for an x-intercept, I know that that's going to be on the y is equal to 0 line. And so in my next step, I'm going to make y 0. I'm also going to distribute the derivative into the bracket factor. If y is 0, on the left-hand side, I'm just going to have minus f at a1, and then on the right-hand side, I'm going to have the derivative at a1, all times by x, minus the derivative at a1, all times by a1. In my next step, I'm going to change the subject of the formula so that I can get x on its own. Taking the first term on the right-hand side to the left, I'm going to get minus the derivative at a1 times by x, and then taking minus f at a1 to the right-hand side, that becomes f at a1. And remember, I still had the derivative at a1 all times by a1. In my next step, I'm going to divide both sides by the factor connected to x. In other words, I'm going to divide all my terms by the factor of minus f prime at a1. And then all that remains now is for me to simplify. When I simplify, I can cancel common factors, which I can do on the left, and in fact I can cancel a common factor over here on the right. So simplified, I can say that my x value is going to be, I'm going to write a1, which was my guess, and then that's minus f at a1 all over the derivative at a1. Now, I don't necessarily have my answer, but what I've got is I've got my second estimate. So if this x is going to be my second estimate, I'm going to call that a2. Once I've got my second estimate, it should help me to find my third estimate, and so on. If I go back to the diagram, we can see how we get closer and closer and closer, and eventually get exactly what that x-intercept would have been. So using my first estimate, I used the first equation of my tangent to my curve. Then I got my second estimate, and from that second estimate, I found the y coordinate that matched with it, as well as the derivative at a2. Then, using that equation for that tangent, I found my third estimate, went back onto my curve to find the y coordinate and the derivative at a3, and so on and so on. And eventually, I end up with exactly what I should have got for my x-intercept for that curve. So we've developed a fabulous new formula to find an unknown x-intercept, which is called the Newton-Rhapson formula.